All right. Hello, class. Welcome to Lecture 6, Part A. In the last lectures, we've restricted our analysis, for the most part, to two-dimensional orbits. So that's where everything we think of is in the orbital plane. So we've tried to parameterize these two-dimensional orbits. We have a central body here, maybe the sun, maybe the stars, or maybe a planet. We have an orbit around that, and we mentioned something about the eccentricity vector being pointed this way and being able to define it using position, velocity, or angular momentum, and so forth. And then we parameterize the orbit in two dimensions with our two orbital elements that we've introduced so far, semi-major axis and eccentricity. And the one that varies with time, of course, which is true anomaly. So this angle that sweeps out from the periaps through, which is defined by the eccentricity vector, to your position vector, r. Now, because these are in two dimensions, right, if r is a position vector, right, it only has two components. This isn't very terribly useful if you're trying to do things like, I don't know, let's say you're trying to you're on Earth and you're trying to point your DirecTV satellite at the DirecTV satellite transmitter, which is actually in geosync, so technically it's sort of like a two-dimensional problem, but you're sort of not on the equator or something, so you have to aim it. So you presumably want to aim this at the satellite, which has a position vector, right, specified presumably in 3 dimensions. Or say you're one of these Starlink satellites buzzing around the Earth, and you want to point your transmitting tower back to a specific point on the Earth, right? Because that's certainly not in geosync, right? So you've got your position vector, and where you want to point it, that's another position vector, and you got to figure out what the relative position is and point your antenna in that direction. Or let's say you're, let's get even more out there. Let's say you're Voyager 2 or something like that. Well out here beyond Saturn. And let's say here's our satellite, our spacecraft. And here's Earth, and you want to keep your radar or communication array pointed towards Earth. Well, in that case, you also have a position vector, and Earth has a position vector. And you want to find the relative position vector and point your satellite, your antenna in that direction. In all of these cases, the problem is very complicated because how do you measure those position vectors? It's not, even if you have the orbital elements and you can predict the true anomaly as a function of time. So far, right, we've outlined the process for getting from time through all these other things to true anomaly and then to R and V. So specifically through the polar equation, where these are scalars and not vectors, of course. And what you're really interested in is the position vector. Now, it turns out that's a harder problem. And why is it a harder problem? Well, it turns out even defining what we mean by position vector is a difficult problem. So say in this lecture, for example, we want to figure out what our orbital elements are, right? Well, we presumed that we know our position and velocity vector, and we got our angular momentum vector and eccentricity vector. And we use those to find our orbital elements. But what did we mean by these position and velocity vectors? What coordinate system are they defined with respect to? Well, it turns out defining a coordinate system in space is actually quite challenging. In fact, there are lots of coordinate systems that we can use to define in space. Some are inertial, and some are not inertial. In fact, you can imagine if you're on the Earth and trying to point your satellite dish, the Earth is rotating about underneath you. And hence, if you just use your local horizon coordinate system, right, where's north, south, east, west, and up, then that coordinate system is rotating. That's sort of well, actually, that's topocentric horizon, but we'll call it Earth-centered, Earth-fixed. But that's not an inertial coordinate system, right? And so, for example, if you defined your velocity in that coordinate system, right, that wouldn't have much meaning because that would be that would be in a rotating coordinate system. And furthermore, the origin of that coordinate system is also moving as a function of time, and so that velocity of the motion of the Earth itself, right, changes what we mean by velocity vectors, right? And of course, the position of the Earth is changing, so the origin of the coordinate system is changing. So r itself is a problematic quantity. So in this part A of the lecture, we're going to go through coordinate systems, how to define them, because it's not trivial, especially for the simple fact that they change over time. Most of the coordinate systems that we use change over time. And specifically, the Earth-centered inertial coordinate system, which we predominantly use changes significantly as a function of year, as we'll talk about. And that can make defining position vectors, even in that inertial coordinate system, problematic, because your position vector in the year 2000, for example, will be different than your position vector in the year 2020, even if they have the same numbers. Right? So we're going to have to do sort of a bookkeeping exercise and define what would be by coordinate system. You wouldn't think it's that hard, right? I mean, what do you need to define a coordinate system? Well, there's two basic ways of defining a coordinate system. There's one, you define it in terms of a plane and a vector. Alternatively, you could define it in terms of the intersection of two planes, and that gives you two vectors. You have to choose one. Or you could just define your x, y, and z axes absolutely, right? Just here, this is x hat, this is y hat, and this is z hat. Right. So three potentially different ways of defining a coordinate system. Now, what it comes down to, or what we'll talk about, is how do you pick these planes, these fundamental planes? How do you pick a vector in space which doesn't change over time? Because most aspects of the solar system are changing over time, and some of them are changing rather quickly. And so there are lots and lots of coordinate systems depending on your particular choice of x, y, and z, or your fundamental planes. So we'll focus on the Earth-centered inertial coordinate systems. There are actually several of them, and we'll define which one we mean later on. And that's great for Earth orbiting satellites. And but we also need to think about, when we're orbiting the sun, heliocentric coordinate systems. And actually, that's even a little bit harder than the Earth-centered coordinate systems. And so once we've defined our coordinate systems in part B of this lecture, we'll come back and then take that two-dimensional orbit that we talked about, right, where you have the eccentricity vector and yada yada, and we'll define the orientation of that sort of ellipse in three-dimensional space. Take this two-dimensional object, an ellipse, and orient it in a three-dimensional space. It's kind of funny, right? I mean, you can think of it as like the orbit is either one-dimensional because it's along a line, right? So really, f, true anomaly, is your only parameter. Or it's two-dimensional in that it's the ellipse, right? Or it's three-dimensional because it's oriented in three-dimensional space, right? So, right, how are we going to define this? Well, this is why we need more orbital elements, and that's what we're going to come back to in the second part of the lecture. So in addition to eccentricity and semi-major axis, which are certainly sufficient to define this two-dimensional or one-dimensional orbit, depending on how you think about it, we need 3 more orbital elements to describe the orientation of this ellipse in 3-dimensional space, where the periapse is pointing, where the normal is pointing, and so forth. And it turns out we need 3 parameters to define that orientation in space, which sort of makes sense. 3-dimensional space, we have trying to orient something, and so that makes some sense. And you would think that eccentricity vector would be the final answer to that, but it turns out that's not what we consider to be our final answer. I mean, if you think about it, right, the eccentricity, well, we'll come back to this a bit. The eccentricity vector, right, it gives you 2 parameters because you can rotate about the eccentricity vector. Right? Anyway, but we'll come back to that. So to start off, right, here's our 2-dimensional ellipse, and we're going to use this 2-dimensional ellipse and take our position vector and our velocity vector and define a coordinate system for them. And then we'll use those position and velocity vectors to get angular momentum and eccentricity, right, which will allow us to define 3-dimensional, the orbit in 3 dimensions, and then we can use those to get the remainder of our orbital elements. We already got A and E from the magnitudes of these 2, and now we'll get also semicolon, argument of periapse, inclination, and right ascension of ascending node. Not in that order, actually. So argument of periapse comes last, actually, but maybe you'll forgive me that little lapse. Right, so let's talk. So we got these 2-dimensional orbits, or 1-dimensional, depending on how you think about them. But of course, orbits in general are not 2-dimensional. In the heliocentric frame, even the planets are not 2-dimensional. For example, let's see, I think I've got Pluto here somewhere. Where's Pluto? So there's Pluto right here. You can't really see it actually very well. I think this blue one is Pluto, but I'm not absolutely sure on that one. Looks about right. Most of the planets, note, that are actually do look sort of 2-dimensional or 1-dimensional, depending on how you think about it. But of course, the other things we see, like comets, are distinctly 3-dimensional orbits. Hale-Bopp, for example, which, by the way, was my first viewing of a comet back in the day when I was at UT Austin. Beautiful Hale-Bopp comet flew by, and you could drive outside of Austin and see it in the night skies. Far better viewing than any comet I've ever seen since. Hale-Bopp was really spectacular. Anyway, but these orbits are 3-dimensional, and so we have to think about what the coordinate system we're going to use is. Well, you see some structure here already, and we'll elaborate that on. For example, there's this natural line to the planets, and so you can think of maybe that's going to give us a fundamental plane, right? So maybe that'll give us one of the fundamental planes that we're interested in. But of course, we need 2 fundamental planes or a fundamental plane and a vector in order to define a a coordinate system in general. And of course, we're assuming that all of our coordinate systems are right-handed. So, right, here's a picture, right, of this orbit in 3 dimensions. Right, so here's say the Earth, right? I don't know where I got this low-quality image, but here's the Earth. Here's the equator, right? And here's our orbit, right? It's that familiar 2-dimensional ellipse, but now you can see it's been rotated about several angles. And actually the angles that we rotate about in order to orient that ellipse are the 3 orbital elements, which we'll talk about later in part B of this lecture, right? Specifically, where we have to define what this inclination is. We have to define where this this periapse occurs in this orbital plane, and we have to figure out how much this orbital plane is rotated about the equator. So that's right ascension, that's inclination, and this is argument of periaps. We'll come back to those later. So again, defined by rotations of this orbital plane into three-dimensional space. But of course, before we define those rotations, we need to orient ourselves so that we know what we mean by x, y, and z, the unit vectors which define our coordinate system. So technically, this given a coordinate system, right, you would think that we would have everything we need from the eccentricity and angular momentum vectors, right? Together, right, they're vectors, so they actually represent 6 components of the orientation. So if you they're not actually independent, but we can ignore that for the moment. But they don't actually give you 6 different degrees of freedom. So specifically, the eccentricity vector, for example, points towards periaps, which is in the orbital plane, and we know that the eccentricity vector is perpendicular to the angular momentum vector. We also know that the eccentricity vector, its magnitude is constrained to be the eccentricity, right? So there's that. And so if we think about what we're given here, our angular momentum vector here, our eccentricity vector here, right? So what are we actually using here in terms of the eccentricity vector relative to the angular momentum vector? Well, what we're using for the eccentricity vector is how much it's rotated in this orbital plane about the angular momentum vector. And then we're using the 2 components of the angular momentum vector. So specifically, we don't have like role of the angular momentum about the angular momentum vector. That's given by the eccentricity. So here we've got, so remember that, we have angular momentum, which is a vector, and which actually defines the plane perpendicular to that angular momentum vector. So the angular momentum vector defines a fundamental plane. And then the eccentricity gives us a vector in that plane, which defines the x-axis, essentially. Well, at least in the perifocal coordinate system. So anyway, that's getting a little bit ahead of myself, because I haven't actually defined the coordinate system in which we obtain these angular momentum and eccentricity vectors. So let me get started with that now. So the coordinate system that we use is the Earth-Centered Inertial coordinate system. So motion in space is relatively complex, right? So we've got, here's the sun, here's the Earth. The Earth is moving around the sun, presumably. But the Earth is also inclined with respect to the sun. So here, for example, we see this is summer. It's the Earth is it's summer because the northern hemisphere is tilted towards the sun. And so that tilt, right, sort of defines a vector, and the perpendicular in this orbital plane defines a fundamental plane. The motion of the Earth around the sun defines a fundamental plane. And then this the equator of the Earth defines a fundamental plane, which doesn't change with respect to time. And then there's 2 different choices for the origin of our coordinate system. There's the sun, the center of the sun, or there's the center of the Earth. And then, of course, buzzing around out here, we've got planets, which are more or less, let's call this Jupiter. And here we've got Saturn, for example. And they're more or less in the same orbital plane as the Earth, but not quite. So they're actually in what's called Laplace's invariant plane. Okay. And so, if you're like in space, you're floating around here, let's say you're this spacecraft over here, right? And you're just looking out at the stars. How do you know which way is the x hat direction? Right, so x hat. Because, right, you want to, you have a position vector, and position vectors give, right, x, y, and z coordinates, and so that would give you the length, the distance in the x hat direction, the y hat direction, and the z hat direction, right? So you can figure out where these positions are, but only if you know what is the x hat direction. So imagine you're this spacecraft and you're like looking out into space and you're trying to orient yourself, and you see the Earth, you see the sun, and you see a couple stars floating around here. And which way is x hat? Well, that's very confusing. I mean, imagine if you didn't have any planets or sun at all. Well, of course, then maybe you would just choose your x hat direction to point towards a particular star and your y hat to be some other star, and then define the z hat as the perpendicular to that plane. But then, of course, that motion might change, right? Or you might disagree with someone who had given you that position vector in the first place. And so that's a little bit problematic. And so, although we certainly use star trackers to orient ourselves, but that we don't use stars to actually define our coordinate system, despite the North Star being fixed in space, or all stars being relatively fixed in space. But in fact, they're all moving around, and that's not what we use to define our coordinate system. Although, actually, the most advanced coordinate system that people use these days is implicitly defined in terms of stars, quasars actually, because they're very easy to pinpoint exactly which direction these quasars are located. So actually they have this table of quasars, and you orient yourself with respect to quasars, but I'm getting ahead of myself there. So that's not what we use for our orientation, and it's not what we use for our Earth-centered inertial coordinate system, because it's Earth-centered, and random stars in the sky, well, they're moving around, and it doesn't make sense to define coordinate systems with respect to random stars in the sky. So we take a slightly different approach, and we focus on what's sort of a natural coordinate system for us. What is the sort of natural z hat direction? Well, as I indicated, there's sort of two unnatural choices for the z hat direction. But let's be particularly Earth-centered, and imagine that it seems to us, right, north is north, right? So north should be towards the North Pole, right? So the z hat, the up direction, is pointing towards the North Pole. And so we define our first fundamental plane to be the equator of the Earth, right? So this red plane here, which of course is defined. There's no equatorial plane if we don't have a rotation of the Earth, right? So what is the equator, right? The equator is the farthest distance from the North Pole, right? Well, what is the North Pole? Well, the North Pole is the rotation axis of the Earth. Right? So the North Pole is the rotation axis of the Earth. And so the equator, well, there would be no equator if we didn't have a rotation of the Earth. And so the equatorial plane is defined by the vectors perpendicular to the rotation vector of the Earth. So we call this North Pole, right? And we can make it a vector. And then the equatorial plane is all the vectors perpendicular to that measurable North Pole. Right, so, well, okay, well, we'll talk about it a little bit. The North Pole is actually not entirely static, it turns out. But for now, we'll imagine that the North Pole is actually relatively fixed because the rotation axis of the Earth it doesn't change a whole lot with time. And it's easy and measurable with respect when you're close to the planet, and so it's a good coordinate system when you're close to the planet. The same logic, of course, is applied to other planets as well, which have rotation vectors, and they all do in our solar system. And so all these other planets, you can define, like, say, for example, Mars-centered inertial coordinate systems with respect to the rotation axis of Mars, for example. So all of these cases, special cases, give us natural z-hat directions, so it's x hat, and all define equatorial planes of the respective planet. The exception, of course, being the sun, because the sun is a huge gas ball, and it doesn't really have a very good rotation axis. Well, I mean, you could argue that Galileo observed the rotation of the sun, so it does rotate. It's just that its rotation axis, as we can best measure it, is not particularly reliable or constant. So there is actually I think it's HEEQ, heliocentric equatorial something something, which is the mean rotation vector of the sun, as sort of measured by someone who spends a lot more time looking at the sun than I do. But anyway, so in each of these planetary systems, there's a natural coordinate system defined in the same way as it is for Earth, using the equatorial plane of that planet, or sun in this case, and defined with that z-hat vector, right? All vectors perpendicular to z. So this gives us our z-hat vector, right? Defines the z-hat vector in these coordinate systems. Also defines the equatorial plane, which is the plane of vectors which are normal to that coordinate system. Notice that the equatorial plane is defined at any point on the Earth, right? Or anywhere outside of the Earth, right? Because it's defined as the vectors perpendicular to the z-hat vector, right? So we could define the plane perpendicular to any of these points, right? So don't get fixated on the fact that the equatorial plane is stuck at the center of the Earth. For everything we do, we don't have to assume that, right? That's not necessary. We need an origin of our coordinate system, this is true, but the plane itself and how we define the x, y, and z coordinates is independent to some extent of the origin of the coordinate system. And naturally, Earth-centered indicates our origin of the Earth-centered inertial coordinate system as at the center of the Earth. Yeah. So actually, I was mentioning the HEEQ, or heliocentric coordinate system, where they use the mean rotation vector of the sun as the z-hat vector. And then the x-hat vector is the line pointing from the Earth to the sun. Again, hard to define fixed coordinate systems on the sun, so they just use the vector pointing towards the Earth there. There's another one which uses the first point of Aries, but we'll come back to that. Right. So you've got one fundamental plane, and so what's the second fundamental plane? Well, one could argue that the second fundamental plane, so here's like the sun. Here I should make it more ballish. It's rotating about its z-axis. And we have the Earth. It's rotating about its z-axis. Not aligned, of course. Remember that. Earth is rotating around the sun. So one could argue that you could use these two vectors to define the coordinate system, the z-hat vector of the sun and the z-hat vector of the Earth. But the z-hat vector of the sun is relatively unreliable, the rotation axis of the sun. And it doesn't really align with the ecliptic plane, so the orbital plane of the planets. And so that's people don't use that, right? It's not typically used. And so we define another vector, right, in addition to the z-hat vector of the Earth. Right? Here's the z-hat vector of the Earth, which is a little bit more reliable. and that is the angular momentum vector of the Earth as it moves around the sun. Okay. So this orbit of the Earth defines an angular momentum vector, right? Basically being the vector perpendicular, right, to the orbital plane of the Earth. Right. So this is a reasonable vector, right? Because, or plane, depending on how you think about it, because it's more or less the same orbital plane for all of the planets. Right? So most of the planets move more or less in the same orbital plane as the Earth does. And so when it minimizes transitions between coordinate systems as you move to different planets. So if you want the Uranus-centric coordinate system, then you can use the z-hat vector of Uranus and the z-hat, which is also not in the ecliptic, and the z-hat vector of this orbital plane of the Earth, which is approximately the same as the orbital plane of the planet. Right? So let's think about this, right? This plane here. So if we draw our solar system here, right? There's the sun. Here's the Earth moving around the sun. We've got the Earth here. Its z-hat vector is there. And then the z-hat vector, right, from the orbital plane of the Earth is pointing in this direction. Right? So, okay, we have two vectors now. Technically, two vectors is enough to define a coordinate system. Right? So, however, which of these is the x-hat direction and which is the y direction and which is the z direction? So we have two vectors. It's enough to define a coordinate system, but it doesn't define the coordinate system per se. We've got to do a little bit more work. Right? So in particular, right, we're going to define the ecliptic plane. We define the equatorial plane as the plane perpendicular to the rotation vector of the Earth. And now we define the ecliptic plane as the plane perpendicular to the angular momentum vector of the orbit of the Earth. Right. So the ecliptic plane, right? Maybe I should use a color here. Right. Is this plane here, and then the equatorial plane is this plane here. Right? And why is it called the ecliptic plane? It's because that's where the eclipse is, of course, because it's defined by the plane which defines the apparent motion of the sun with respect to the Earth. Right? So naturally, if an eclipse is going to occur, right, that is going to block out, right, the sun as viewed from the Earth, or a transit of the sun for a smaller planet. Eclipse for a moon, right? That has to occur in the ecliptic plane because otherwise, right, it wouldn't block, right, the view of the sun, right? Because the view of the sun is it always lies in the ecliptic plane. So that Earth-Sun position vector, right, always lies in the ecliptic plane. So in order to create an eclipse, you have to move into the ecliptic plane. So here we go. Okay, we've got the ecliptic plane. Now we've got to we're most of the way there. We've got two fundamental planes, and now we just have to define what we mean by the x vector. So our z vector is going to be the perpendicular to the equatorial plane, and now we're going to use this ecliptic plane to define an x-hat vector. So we'll come back to heliocentric coordinate systems later. Yes, so I should mention, of course, when I said that all of the planets move approximately in the ecliptic plane, it's approximately true, but it's not absolutely true. So for example, if you remember, There's the ecliptic plane. You view it in the night sky. Here's the night sky. And the motions of the planet can be a little bit irregular, right? Looking like that. So that's because the orbital planes of these planets, for example, Mercury, are not precisely aligned with the orbital angular momentum vector of the Earth, right? The angular momentum vector of Mercury is slightly different. But they're all approximately the same, so all of the current planets, excluding Pluto, are all within plus or minus 6%, 6 degrees of this ecliptic plane. So they don't move far out. And in particular, Jupiter, which is the biggest planet, contributes most to the angular momentum of the solar system, is only about 0.5 degrees off of the ecliptic plane. Which brings up another obvious choice for the second fundamental plane, which is not the ecliptic plane of the Earth, but rather the what Laplace's so-called invariant plane, which actually makes a little bit more sense. It's more invariant as opposed to the orbit of the Earth, which actually changes over time, which is the angular momentum vector of the n-body system, which is the solar system, right? So remember, we talked about n-body problems. For an n-body problem, the angular momentum vector is invariant. And so actually in Laplace's system, right, you take all of these, the n bodies in the solar system, and they form an angular momentum vector. And that angular momentum vector is our fundamental plane in Laplace's invariant plane. Fortunately, right, the difference between the invariable plane and the ecliptic plane is not substantial, only around 5 degrees. Or maybe 5 degrees. Or is it 5.5 degrees? I think, well, I know, it says 5 degrees, so I'll say it's 5 degrees. So technically, right, Laplace's invariable plane is a better choice than the ecliptic plane. But since most of our coordinate systems are based on Earth observations, it's much easier for us to say, for example, observe the transit of the sun through the sky than it is to observe this mysterious angular momentum vector of the solar system, especially because it's hard to measure the mass of planets, so even to determine what that invariable plane is rather challenging. So this requires mass of the planets to determine. Right. So if we're coming up with this thing from scratch, we're like, in the olden days, it's much easier to observe the ecliptic plane and the rotation in the equatorial plane. Sorry, those are drawn the same. So in the olden days, it's much easier to observe the rotation vector of the Earth, basically because you have a compass, which is pointing in that direction. And it's easy to observe the ecliptic plane because that's where the sun, right, is in the sky. So two obvious orientating vectors on the Earth for defining a coordinate system. So this was the first coordinate system. Of course, there's much more modern ones now. People use, but we'll talk about those later. Okay. So we've got here our two fundamental planes. We've got the ecliptic plane here in blue, and we've got the equatorial plane here in not blue, so white. And fortunately, of course, these are not co-located, right? So they're inclined with respect to each other. They're not the same vector. So that's the equatorial plane. This is the ecliptic plane. And as I said, right, it's easy to observe the ecliptic plane because this is where the sun is in the sky, right? With respect to the other stars, mind you, not just absolutely in the sky, because of course the Earth is rotating, but where the sun lies with respect to the other stars, right? So in particular, you have the zodiacs, right? Here's the stars in the sky. It's going to take a while to draw lots of stars. And here's the motion of the sun through those stars. Actually, it typically appears to move this direction. So there's our sun, and it's moving through the stars. And so that defines an obvious plane for us to use. So this plane is, of course, inclined with respect to the equatorial plane because they're not the same, right? And that inclination, that difference, has a special name, the inclination to the ecliptic. I believe it's also known as the obliquity to the ecliptic. There's no difference between the two. And it does change a little bit with time because the Earth's rotation axis does precess over time, which is a bit of a problem for keeping track of in modern coordinate systems. We don't. This is actually not a modern coordinate system, but it does change over time. It's currently, however, for back of the envelope calculations, 23.5 degrees. Right? So that's the inclination to the ecliptic. Very important number. We use it quite often when determining vectors. So here we go. Here we have an Earth-centered coordinate system. One vector defined by the rotation vector. One vector defined by the perpendicular to the sun's plane, sun's motion. Right? Notice, however, I'll make a couple comments, right, on this picture here. Right, so this is from the Earth's perspective, right? If we draw the same picture from the sun's perspective, right, then I have to make a little bit more room. There's a sun. Here's the motion of the Earth about the sun, right? And here is sort of the Earth here at 4 different points. Right? And you can tell what time of year the Earth is at these various points by the direction of this north celestial pole, the z-axis, or the rotation vector of the Earth, right? So particularly if the rotation vector is pointing towards the sun, right, then the north pole is pointing towards the sun, and we have that this is summer, typically defined as summer, northern hemisphere summer. Likewise, if we're on the opposite side, this rotation vector fortunately doesn't change much over time. And so in the northern hemisphere, we have winter. Okay. And then that's because, right, of course, the sun apparently spends more time in the sky here when we're pointing towards it than when we're pointing away from it. Right? And then, of course, we have the equinoxes. Right, where the sun appears directly along that equator. Right, so if you're on the equator, the sun is directly overhead. Right, at these equinoxes, or these equinoxes. So here's what we got there. There's 1. There's 2. And of course, this is winter, so this obviously must be a spring equinox or vernal. And this is summer, so this also must be autumnal equinox. Okay. So there's some discrepancy here, right? So here at the vernal equinox, right, what's going on, right? So in the winter, right, as measured from the northern hemisphere, where presumably many of us are living, here's the northern hemisphere, in winter, right, the sun appears to be below the equator, right? It appears to be below this equatorial plane. I mean, that doesn't mean you can't see it, right? Because remember, we can transfer these planes to any point here. But it appears to be below the equatorial plane of the Earth if you measure due east. Right? And then it slowly rises, right, through the zodiac, to the vernal equinox, where it appears directly towards in the equatorial plane, and then it moves up into summer, where it's above the equatorial plane, and then it moves back down. So this the vernal equinox is we consider it to be an ascending node of the sun, because it appears, right, in our Earth-centered coordinate system, right, where the sun is orbiting the Earth and not the Earth orbiting the sun, it appears that the sun is rising, right, as opposed to setting right here. This is when the sun is setting, and this is when the sun is rising. And so, generally speaking, we prefer the ascending node of the sun's orbit around the Earth as opposed to the descending node, where the sun is going below the equatorial plane. And so we're going to be biased going forward towards this vernal equinox as opposed to the autumnal equinox, which we more or less ignore. And in fact, the point at which the sun is rising is what we're going to actually be calling our x-hat coordinate. But we'll get to that in a second. So, as I said, right, the apparent path of the sun through the zodiac, right, goes from below the equatorial plane in winter to above the equatorial plane in summer. And remember, two orbital planes, right? We're going to define our z-hat axis to be the due north, right? North pole, if you want, or the North Star, if you think that's fixed in space. But of course, that's actually fixed as opposed to the rotation vector of the Earth, which is not fixed. But anyway, so that's the z-hat axis. So we have two planes now, and we have two choices for what our x-hat direction is. The first one is the autumnal equinox, and the second is the vernal equinox, because those are the 2 points where these two planes intersect. Okay. As I sort of justified, however, we tend to prefer ascending nodes, and so we've arbitrarily chosen the vernal equinox to be our x-hat direction. Right. So there are two equinoxes, right? Two obvious points for x-hat direction, which are perpendicular to z-hat, right? Notice that no other point on this plane is perpendicular to z-hat. So we have to choose one which is perpendicular to z-hat. And so we choose either one of the equinoxes, and we prefer the vernal equinox because it's perpendicular to the, because that's the ascending node. So this was actually chosen by Ptolemy, I believe, if I remember correctly. And it's called the first point of Aries. Notice that Aries is not Aries as in the god of war, it's Aries as in the ram, which I don't know my astrology well enough to know why this. I think it's like from Jason and the Fleece or something like that. Anyway, Ptolemy made up all these names for all these initial zodiac constellations and chose Aries as one of them. And it's called the first point of Aries because as you observe it in here's the constellations, here's Aries, here's like Pisces, I don't know, Pisces is over there somewhere. The sun, right, appears like this. It appears to be going like this, right? And this intersection back in the time of Ptolemy used to occur at this intersection. This is Aries. This is, I don't know, some other constellation. This is the sun, and it's moving that direction. Again, from northern hemisphere to southern hemisphere. Notice it's going in a different direction than I've drawn it on this picture. And that's, of course, because we are looking at this picture from the outside, and Ptolemy was looking at this picture of the zodiac from the inside, right? So he was viewing it this way, and we're viewing it the other way. So the image is reversed. So that's why it's going from the right to the left as opposed to the left to the right. Yeah. So anyway, this was the first point that it entered the constellation of Aries, and it happened to coincide with the vernal equinox that year, and so that was that's what we called the first point of Aries. Right. So the first point of Aries is a very, very important vector, not least because it changes with time and is hard to fix, but so it gets its own special symbol. I think it's looks like a ram, something like that, for Aries, the ram, who no one knows about except for the fact that it's the first point of Aries. So does first point of Aries lie at the ascending or descending node? it lies at the ascending node as we view it from our heliocentric Sun orbiting the Earth coordinate system, which of course Ptolemy believed in at the time. Now, of course, we can think about is the Earth rising or setting with respect to the Sun? But again, that doesn't make a whole lot of sense because the Sun doesn't pay much attention to the Earth's equator. But I suppose if we impose the Earth's equator onto the Sun, we would be actually setting at that point, right? Because here's the path of the Sun, and the Earth is going to appear to be going down, I guess. Anyway, so it's all relative, but technically, I guess we should consider it. Well, I don't know. Depends on who you ask. I'll call it an ascending node. Ptolemy called it an ascending node, so we'll stick with Ptolemy. All right. So here's a nice little video we have, which illustrates these various vectors better than my scribbles. So here we've got the sort of coordinate system here. Let me put it on repeat. Right. So this is the equatorial plane of the Earth, right? What you're seeing here, right? There's the equatorial plane of the Earth. These lines, that's the equatorial plane of the Earth. And there's the rotation axis of the Earth meeting here at this dot up here. And what you see now is the blood filling the solar system is the motion of the Sun around the Earth, or the motion of the Earth around the Sun, depending on which you prefer to think about it. All the blood drains away, and we see the intersection of that apparent motion of the Sun around the Earth as this sort of, what do you call it, ring around the tub, ring around the, yeah, I think it's something like that, ring around the something, I don't know, there's some word they used to use for when you take the dirty bathwater out of a tub. In any case, so there's, I can just go up here a little bit. Right. So this apparent motion of the Sun around the Earth around the Sun, right, gives us the point of intersection here. Well, actually, the point of intersection for the vernal equinox is over there, and so that's where we're going to define our x hat vector. Let's close that up. Get back to our lecture notes. So again, right. Here we've got some the motion illustrated for this coordinate system. So the problem is that the angular velocity vector of the Earth is not even remotely fixed. Did I say here? Where? Oh, yeah. Moves by 1 degree every 72 years, which is a lot, right? The first point of Aries moves at that intersection of the ecliptic and equatorial plane moves quite a bit. So if this is the, actually let's make this the rotation vector of the Earth, z hat. Right. The forcing, there's this forcing vector, and there's a natural nutation of that of the rotation of the Earth, which causes this this rotation vector to nutate and precess. Right, so its apparent motion in the sky looks something like this. Right, so it moves. This nutation has a period about 18 years, and this secular motion, this precession, has a period of about 25,000 years. In any case, it's moving, right? And from the time of Ptolemy to now, it's moved quite a bit. So in particular, the first point of Aries, right, now no longer points anywhere near Aries. It points to Pisces, I believe, at this current point of time. Here you can actually see it moving from the time of Ptolemy approximately. That's a little bit before Ptolemy. Here's the first point of Aries at Ptolemy. To 970, and then to 1970, and I don't know, maybe it's moved a little bit to 2020 over here. Right. So this is the equatorial plane of the Earth. Let's just to orient a little bit. So this is actually the equator. So if you try and orient, right, that's our z hat direction, and then the ecliptic, as we view it in the night sky, is this line, right? And so the sun moving through the ecliptic is going to be moving from south to north. And so the sun is actually going like this, right? So, and then that intersection point, right, is the first point of Aries. And that intersection point is changed over time, right? So now the sun, well, now here the sun rises above the equatorial plane at the Pisces constellation. So it's like really should be called the first point of Pisces now, but it's not. So what are you going to do? So we can't change the name every 1,000 years, right? I mean, it gets ridiculous. But so anyway, point in fact, this is a coordinate system that's been used since essentially the time of Ptolemy. It's not the best coordinate system because it's not truly inertial and has been replaced, of course, in more recent times by much more reliable coordinate systems, which we'll talk about in a second. But that's the one, that's as a first approximation, and in this course, that's the only one we'll really be using, is the Earth-Centered Inertial Coordinate System. Right. Right, so again, right, summary, north direction, z-hat direction, rotation vector of the Earth. X-hat direction, the direction to the sun at the vernal equinox, right? So the vector pointing towards the sun at the vernal equinox, right? And then the third coordinate system we get by the right-hand rule, x, y, z. So there's our, you can't see it, there's our z, there's our x, and I was through some weird permutation on my hand, right? So there's my thumb. You can do it yourself, right? Thumb, middle finger, and index finger. So the y-hat vector is perpendicular to those two vectors and points in a right-handed coordinate system that way. Okay. So we don't fuss too much with the y-hat direction. Now, as I mentioned, the Earth-centered inertial coordinate system, as we've defined it, using the first point of Aries, is relatively unreliable because the first point of Aries changes over time due to the precession of the Earth, mostly because the Earth's rotation vector is unreliable. It precesses and it nutates. So if you're actually doing coordinates, like, for example, calculating GPS coordinates, right? For example, GPS is how we typically orient now in space. At least, well, yes, even satellites use GPS coordinates. Anyway, but the data you get, right, you have to figure out where all the GPS satellites are in order to calculate a position vector. For example, right? I mean, it applies to all, basically, position vectors. But so if you're using the Earth-centered inertial coordinate system, which people typically do, you have to be a little bit more precise and define which x-hat vector you mean. So in particular, the most common one is the J2000 coordinate system, right? 20 years out of date now, but that's okay. Which was defined as the vernal equinox on January 1st, 2000 at 12 o'clock terrestrial time, right? Which, is kind of dodgy because, okay, first of all, there was no vernal equinox on January 1st, 2000, right? The vernal equinox occurs about 6 months later than that. That's midwinter, or not even midwinter. So, but that's okay because what we're looking for is the intersection of the equatorial and ecliptic planes at that time. So it's not actually, don't fuss because it's not on the vernal equinox. It's sort of the predicted vernal equinox on that date. And then terrestrial time is sort of a more accurate version of UTC, which is a replacement for GMT. So it's noon at GMT essentially at 12 o'clock on January 1st, 2000, where that intersection occurred. Right. So yeah, so that's the definition of J2000. Then of course, lots of people say J2000 is 20 years old, so I'm going to just use a different coordinate system, a more recent one, And so there's the alternative, which is true of date, where you give the date of your coordinate system and then calculate for the rotations and various precessions of the Earth. Some other Earth-centered inertial variants you may see occasionally. We just described the J2000 TOD. Another one is mean of date. Mean of date, remember there's those nutations, right, which are relatively high frequency, 18 years. So that's a sort of a problem sometimes with these true of dates. Mean of date sort of takes the average through these rotations, these nutations. So that's mean of date, and then so that's the equivalent for true of date, and then M50 is the equivalent of J2000, and right, there's one more which we occasionally run into, the geocentric celestial reference frame, where the z hat vector is not the angular velocity vector of the Earth, but basically the ecliptic. Technically the North Celestial Pole, but we can think of it as the ecliptic. So it's like the equivalent of the same. It's the same coordinate system. Still, first point varies as the defining x hat vector, but now our z hat vector is the ecliptic plane essentially. So instead of using our z hat vector as the angular velocity vector of the Earth, we instead use the angular momentum vector of the Earth around the Sun as our z hat coordinate. Right, same difference. Remember, the first point of Aries lies in both the ecliptic and the equatorial plane, and so it equally well defines the x hat vector in this plane as well, because it's perpendicular to the angular momentum vector. There are lots more coordinate systems. Really too many to describe, although I will give it a shot. I'm just going to go through them real quick. In order of perhaps the ones we come across. So Earth-centered, Earth-fixed is the one we probably come across next most often. And that's not an inertial coordinate system, but it rotates with the Earth with the z hat vector pointing towards the North Pole and the x hat vector pointing towards Greenwich. Right? And y hat perpendicular. Next, the Greenwich meridian, not actually towards Greenwich, because Greenwich would be up here, but the Greenwich meridian, meaning like this one. So, yes, that, yeah, okay. So its longitude is 0, for example. Perifocal, this is actually sort of a 2D coordinate system. It's defined with the orbital plane. We haven't, right? So it's in the perifocal, right? The x hat direction is pointing towards the eccentricity vector. The z hat direction is perpendicular. It's the angular momentum vector of the orbit. Frenet, actually we don't see Frenet very often, except when we're talking about drag. That's the velocity vector of the orbit is the coordinate, is the x hat coordinate there. Topocentric horizon, that's even more Earth-centered than normal. So in the topocentric horizon, let's see, here's our Earth again. So it's defined differently for every place on the Earth. So for in that case, north, east, and then up. So actually in that case, I believe I forget which actually is x and y, but those are the three directions: north, east, and up. Topocentric equatorial modifies this one a little bit to make the equatorial plane the fundamental plane, and then north also is the vector, right? So equatorial plane, and then north. I'm confusing these a little bit. So that's the topocentric equatorial. I've got like a whole list of them here on the next one. We did this one, did this one, did this one. Satellite radial. We encountered that one actually in a previous lecture. So it changes all the time, right? So definitely not inertial. Its x hat is the r hat, instantaneous r hat vector. Right. So when we were calculating angular momentum, proving Kepler's second law, we used actually the satellite radial coordinate system. And then, of course, the z hat is perpendicular to orbital plane. Let's see what else we got here. Horizontal coordinate system, similar to topocentric, but uses azimuth and altitude. Heliocentric coordinate systems, we've got a few of them here. We talked about one already, this HEEQ one. The heliocentric Aries coordinate system, again using the Earth orbital plane, essentially the ecliptic. And the vernal equinox. So this is actually closest to our standard definition of ECI. But of course, it's sun-centered, right? Heliocentric, so sun-centered. And then the variant on that, also heliocentric, so sun-centered. The origin is at the sun. Uses, again, the ecliptic, again. But then the other vector that it uses is not the first point of Aries, but the instantaneous Earth-Sun vector. So if here's the sun, here's the Earth moving around there. The orbital z hat is that way. And then the x hat points towards the Earth. That's the heliocentric Earth ecliptic, sort of Earth rotating one. That's sort of the equivalent of the satellite radial for the Earth. What else we got here? A barycentric. This is actually closest to the one that people use most often now. So the origin is the barycenter of the solar system, so not just the Earth, but the barycenter, which is actually invariant as opposed to the Sun, which actually moves a little bit. The z hat is the north celestial pole, and again, the x hat is approximately the first point of Aries. So if we're using ECRS, it's actually ECRS is defined using quasars. So you have these very long baseline interferometry observations of these quasars, which emit sort of these signals in space, very pinpointed very accurately, and so it's actually technically designed with respect to these quasars, but it approximately corresponds, the x hat approximately corresponds to the first point of Aries in the J2000 coordinate system. Again, in ECI, J2000 is the most common coordinate system that people use. We can go to outside the solar system, so there's the galactic coordinate systems. So for example, the galactic equator, that's sort of the disk of the Milky Way. So here's the Milky Way, here's the center of the galaxy. So the center of the galactic coordinate system is that black hole at the center of the galaxy. And then the arms of the Milky Way are, that's my, I think they're actually backwards. There's the arms of the Milky Way galaxy. They form an approximate plane. And so we have the galactic equator, right? And you can calculate if you like, the inclination of the galactic equator to the ecliptic plane, if you like. But we don't need to, right? So it uses the sun galactic vector as its other vector. So the vector from the center of the galaxy to the sun, wherever, I don't know, where's the sun? It's over there or something like that, as its reference vector. So lots of coordinate systems. Again, if you're serious about astronomy, ICRS is the one that people use now, defined by those quasars. And it approximates, however, the first point, it approximates the J2000 coordinate system. Well, not the ECI J2000. It approximates the heliocentric Aries ecliptic coordinate system in J2000. And so it's approximately that one. Anyway, so it's a very complicated relationship. As you can see, orienting yourself in space is non-trivial. And in fact, when I wrote my space elevator paper, I had to I think go through at least 6 coordinate systems to translate these vectors for interplanetary mission planning purposes. All right, well, so I think that at this point, we've defined our coordinate systems, or actually particularly the ECI coordinate system, and we'll just assume that's J2000. And so we're ready now to define, we know what we mean by position and velocity vectors. And so armed with those position and velocity vectors, we're going to start defining other things. We can know how to define our angular momentum and eccentricity, and then we'll use that to define our orbital elements. And ultimately propagate our orbit to get future position and velocity vectors in space. And for targeting and orientation and navigation and all the things that we actually want to do in space before we get to the end of this course. So at this point, I will cut it off and come back next time with those additional orbital elements.